morning, class. So we have, there were some announcements I made. I just want to make sure you're on top of things. Because we have homework due tonight. I think you know that. And so you're aware the next homework is due like a little bit sooner. It's due next Wednesday. Okay. And there will be one due the following Wednesday after that. But we also have upcoming, I announced was a week from today, we'll just have our first little quiz. There are going to be just a small number of quizzes this semester, just 3. A little bit, the intention is a little bit before each exam, we'll have a little quiz in class. This is supposed to be about 20 minutes, in class, at the tail end of class. And then, so that's coming. What it covers, I posted, but it's everything so far up to and including what we're doing with Diophantine equations today, as well as what we'll keep doing related to them, something called the postage stamp problem today. That's that. Oh, and then the week after the quiz, by the way, is when our first exams. Details are coming. Okay, just try to be mindful of the calendar. You have any questions or concerns or anything? Okay, we were a little bit in the middle of something. This is our main theorem about Diophantine equations. And I stated it, and maybe it was a little bit shorthand, but just to remind you that everything's an integer here, and we're talking about solving these Diophantine equations with integer solutions. So integers, x comma y, that satisfy them. And the one thing we proved, which we've already taken care of statement 1 here, is that a Diophantine equation like this will have integer solutions if and only if the GCD of these 2 coefficients is a divisor of the right-hand side. Okay, we already proved that. And then when it has solutions, it actually has infinitely many, and they all have this specific form. And so we haven't quite proved this yet. So we were doing a special case that we're going to lean on today to finish the proof of that. Okay, so once solutions exist, once you know you have one, you actually have infinitely many, and they all have this specific form where these formulas here have some kind of parameter in them, t, and t is allowed to run over all the integers. Okay, and that precise collection of pairs gives you all the solutions. Okay, so what we did do, let me remind you of something we did prove last time. First of all, we proved statement 1 and also the following lemma. This is what we ended with. The situation or the thing we did prove is that every solution of this equation, this Diophantine equation where the right-hand side is 0, this has the form which is x is b over dt, y is minus a over dt for some integer t. Okay, and so here, sorry, I was sticking with the notation over there, which is that d was the GCD of a and b. Okay, this is what you would call a homogeneous Diophantine equation. It has a right-hand side of 0. And in general, when there's not a 0, it might be called non-homogeneous or inhomogeneous. And if you've heard these words in the past, then what's going on here might resonate a little with you, because like in different things you do, like linear algebra, also differential equations. When you solve non-homogeneous things, one of the things you often do is find like one solution, and then from that you build a general solution in a certain way. And that's actually kind of what's happening here. There's supposed to be one known solution, any one you could find, and then once you have that, you can assemble the general solution out of it. Okay. So, all right. Now we proved the lemma. We proved statement 1 over in that theorem. Now we actually have to finish and prove statement 2. Okay. So we're going to deal with this thing now. So we have to do the proof. Theorem 3.1, part 2. That'll finish the theoretical portion of dealing with Diophantine equations. Okay, so anyway, what I guess we'll start with is, in statement 2, you're supposed to know a solution. So let's just begin by saying that's what we get to assume is that we have a solution. So suppose x naught y naught is one solution that is known of ax plus by is equal to c. Okay, now what this is asserting is that, this description of xy pairs is the complete solution set. So there's actually two things that we should really check about this. First of all, it is implying that anything that looks like this is a solution. So we actually have to confirm that these formulas define solutions. That's part of it. But then the rest of it is that it's asserting that these are all the solutions. So any arbitrary solution of this Diophantine equation has to fit this form. So there are actually two things we have to do. We have to first check that anything defined this way gives a solution. Okay, so first, what we'll do is that if you had anything that looked like this, where t is an integer. So first we must show that anything that looks like this is a solution to the equation. Okay. Now, if you're tasked with verifying something is a solution, that's actually kind of simple. It's like you just plug it in and make sure it works. Okay. If you want to verify something's a solution, put it in the equation, make sure the equation's satisfied. Okay. So to confirm this, what you would do is you would, let's verify it's a solution. So what you do is take this x and this y and insert it into the left-hand side of the equation. Right? So the x is a thing that looks like this, and the y is a thing that looks like that. And we have to justify that it equals c, and therefore it satisfies the equation. Okay, so don't say it equals c because you don't know it equals c. You have to show it equals c. Right? So let's work with this expression and try to simplify it and show that it equals c. Okay, and so if you work out all these terms, you expand this all out, you have an ax naught plus b over, ab over dt plus by naught minus ab over d times t. And so these would cancel. Right, and you're left with ax naught plus by naught. Right, and x naught, y naught, that pair was assumed to be a solution of this equation, which means when it gets plugged into the left-hand side, it does equal c. Right, so this thing does equal c precisely because x naught, y naught is a known solution. Okay, so that confirms that. That's like half the proof. Well, the easier half, I guess, but that's like half. We have to do two things. That was one of them. Right, so we first check that these things are always solutions. And now the rest of the proof is to take an arbitrary solution of the Diophantine equation and try to explain why it must have this form. Okay? So this is kind of the start of an independent chunk of the proof. Okay, so next up, what we would need to do is we'll show that every solution has this form. Okay, so what we're going to do now is just suppose somebody just hands us a random arbitrary solution. So you suppose x comma y is an arbitrary pair of integers to this Diophantine equation ax plus by is equal to c. So all you know about x and y is that they're integers and they satisfy this equation. Okay, and so this is where we need our lemma for. Okay, so here's the idea. Now, what we do still have in this whole general context is this thing, right? So we still have like a known solution. And so the idea here is an idea that, again, might resonate with you if you've heard a lot of discussions about homogeneous and inhomogeneous things. And there's a general principle when you're dealing with these kinds of things, which is that differences of non-homogeneous solutions give you a homogeneous solution. And so that's the inspiration for what we're about to do. So what we're going to consider is the following pair of things. Let me see if I give them a name. Well, yeah, I'll give them a name. Let's make some notation. I don't know. Let's put a tilde on it or something. So let's consider the difference. So let's take the x that was handed to us minus the x naught we know about, and y tilde. Let's take the y we were given minus the known solution, y coordinate, like that. So the point to consider about these things that we'll show is they actually satisfy this equation. Okay. So then what happens here is if you look at ax tilde plus by tilde, let's evaluate this and simplify this. Okay, so this looks like a x minus x naught plus b times y minus y naught. Okay. Yeah. Okay. And then you do some algebra to this, expand all these terms out. What you should have is there's an ax plus a by from these parts. And then there's a minus ax naught minus by naught. So let's write it like this. So there's four terms. You could expand and rearrange them, and it would look like that. And the thing is that we do know x naught, y naught's a solution to ax plus by equals c. So this thing equals c because it's a solution. Right? Likewise, x naught, y naught is also a solution to ax plus by equals c. So when you put it into that expression, it simplifies to be c. So that is also c. So this is c minus c. Oh, and that's 0. Say that point too. Right? So what happens is if you take x tilde y tilde and put it into this left-hand side here, it gives you 0. So the x tilde y tilde fits into the discussion of a lemma here. Okay, so what this means then is, well, it shows, just make it a little plain right here, that this is true. We've just shown that's true. And so now you can hit it with the lemma and say by this lemma right over here, if you have such a thing, then the solution has to have this very specific form for some integer t. So what happens is that x tilde is b over dt, and y tilde is minus a over dt for some integer t. Okay, and then that's basically supposed to be pretty much the end. What happens is just put what x tilde is back into this, and y tilde. So this is x minus x naught is b over dt, and y minus y naught is minus a over dt. And if you just solve for x and y, you're done. So x is x naught plus b over dt, and then y is y naught minus a over dt. Okay, and that's the end. This thing in the way. Can't move it because it just goes right back. Tried it, doesn't work. Sorry. Anyway, that's the end of the proof. Because what we've done is we started out with an arbitrary solution, and where did we get to is we justified it has this form. Okay, so they all have that form. End of story. End of proof, end of theorem. And so that's completes the main result about these Diophantine equations. Okay, so it's good we proved it, so we know it's true. And then it is a practical sort of thing because it gives you the formula for the solutions of any one of these Diophantine equations, and remember how it's built. If you're going to take advantage of this formula, you need to find an x naught, y naught. So let's maybe just summarize what we would do. Practically speaking, if we were solving the Diophantine equation, linear Diophantine equation, by the way. Well, I mean, I guess first step you want to do is just to break it down a little bit. Make sure D divides C, right here, D is the GCD. Right, if that's not true, there's no solutions. If it is true, there are solutions, right? And then the next step, I guess, would be to take advantage of the extended Euclidean algorithm. To find one solution. X naught, y naught. Now what the extended Euclidean algorithm actually does for you is it gives you a solution to an equation like this where the right-hand side is D, actually. Right? That's exactly what the extended Euclidean algorithm does. It gives you one solution where the right-hand side is D, not C. But when you know C is a multiple of D, you can just multiply both sides of the equation by the appropriate multiple to turn the D into a C. And that's where this solution comes from. So, and then, anyway, once you've done that, that's basically the main thing. The general solution is given by the formulas that we were just working with. So x naught plus b over dt, and then y is y naught minus a over dt. But that's a bit of a summary. And we could do one example just to make sure we're happy with how to solve these things. Okay, so here's an example. Talking about Diophantine equations, so when I say solve it, I mean we're going to find all integer pairs of solutions to it. So here, you know, A is 12, B is 45, you know, C is 30. You need to identify these things. But the GCD of A and B, well, is 12 and 45. Okay, I mean, you might want to take a moment to figure that out. I mean, we could use the Euclidean algorithm if you need to, but it's 3. Okay, it's going to be 3. So that's going to be the GCD. And so anyway, then the first thing you should think about is once you know the GCD, just make sure the right-hand side is divisible by it, which it is. Right? 3 is a divisor of 30. So solutions exist, and we can get to work finding them. And so we need to do the extended Euclidean algorithm. I mean, maybe you don't necessarily need to do it. The extended Euclidean algorithm lets you write 3 as a linear combination of 45 and 12. And maybe if you think about it for a second, you can figure out how to do that without too much effort. Because you can make 48 out of 12, right? And then somehow cook it up so you have 48 minus 45, and that gives you 3. I mean, so you could maybe just possibly just figure it out by inspection or whatever, take a moment. But the Euclidean algorithm is foolproof, and it will always work. So let's just do that. So if we're going to do the extended Euclidean algorithm to 45 and 12, you would divide 12 into 45, goes in 3 times with a remainder of 9. And then you could divide 9 into 12. Goes in once with a remainder of 3. And remember, these things kind of shift like this. And then you would divide this 3 into 9. It goes in 3 times with a remainder of 0. And so that, I mean, that's what proves your GCD is 3. But we also need these equations in the extended Euclidean algorithm. So 3 is 12 minus 9 times 1. This one says. All right, this is the one you actually want to work with. You take the GCD expressed here as a combination of these, and then actually insert this in place of 9. So maybe we'll just do it right here. All right, so what this would tell you is, right, 9 is 45 minus 3 12s. There's a 1 there. Okay, and now this is a linear combination actually of just 12s and 45s. So group them all together. And what you should have here, as far as 45s are concerned, no, let's write 12s first. 12s are first up here. Right, so what do we actually have is 4 12s. And then there's just minus 145. Okay, this is probably what you were thinking about if you're trying to make 48 and take 45 away, right? There it is. Okay, but anyway, that's algorithmically producing it. So x naught is 4, and y naught is negative 1. That's one solution to this Diophantine equation. Right? And then all you really have to do is write the general solution down right from this formula. Okay, just note like what there's going to be a little bit of division. Okay, so our general solution. Right, so x is supposed to be x naught plus b over d. Right, so just don't mix things up. But 45 was b, and d is 3. So 45 over 3. Right, and then y is supposed to be the y naught we found minus a over d. So it's 12 over 3. Right, so what this actually looks like is 4 plus 15t. And then y is negative 1 minus 4t. T is an integer. So that's all the possible solutions. Yes?
Shouldn't x naught and y naught be multiplied by 10?
Oh, gosh. Whoops. My mistake. Yeah, I missed a step. Sorry, I got carried away. So what I actually did, by the way, is wrong. But I solved for the equation if you have a 3 on the right. I'm sorry. So we missed a step. Eli, well, okay. Anyway, let's fix it. Sorry. Thank you. So what did we actually do? Let's just back this up and fix it. Okay. So what we really did over here was we found that right. So this was 3. Right. So 12 times 4 plus 45 times minus 1 was 3. Right. And then the point was we had 30, which I sort of forgot about. So what you want to do is multiply by 10. And when you multiply both sides by 10, right, so let me not call these x naught, y naught. So when you multiply both sides by 10, you would want to like absorb that into these coefficients, right? So you have 12 times 40 plus 45 times negative 10. Okay, that gives you 30. So sorry for this. The x naught is the 40, and the y naught is the negative 10. Right, so this is a solution to the actual equation that was given in the example. Right, there it is. And then that gets inserted up here. Sorry for messing this up. So this then coming up here, fix. Okay, so we have 40 and negative 10. 40. Think it looks suspicious, let me know. Thanks. Okay, is it okay? Okay. So anyway, that's what we found. One solution. These are all the solutions. If you want to write some more down, just plug in some t's, for example. Okay. Okay. very specific, nice example of a Diophantine equation. There are also nonlinear Diophantine equations. There's also linear Diophantine equations with more variables. We're not going to really get into all that, but this is the simplest sort of Diophantine equation, and that's how it works out. Okay, so we're going to, we will move on to a very related thing, which is maybe a little bit fun to think about. So, the next thing, the next section is something called the postage stamp problem. And this is just the motivation here is comes from very unrealistic numbers from a long time ago, but we'll just work with it because they're nice. We're talking about stamps. Suppose the post office sells two types of stamps. Okay, and suppose they have 3-cent stamps and 5-cent stamps. For whatever reason, but these are the only kinds of stamps you could buy. And let's say that when you need to mail something, you might just you need a certain amount of postage on it, perhaps not just 3 or 5, but something more. And the idea is supposed to be that you have to maybe put multiple stamps on your mail to get the right amount of postage. Okay, so here's the question: is what postage values could you actually put on your mail? Like through a combination of these stamps, is the idea. So, like for example, you certainly can't put 1 or 2 cents on, right? And you can't put 4 cents on. You could put 3 cents and 5, of course. And then you could think, well, you can make 6 cents of postage because you could do 2 3-cent stamps, okay, right? So you can think a little bit about, some examples. So here's some possible postages, and let's just use the word feasible to describe whether or not it's possible. So, let me just make a little chart for this very simple example, and then walk through some possibilities. Perhaps that keeps going. But so let's just put some X's or checks or something. Like obviously you cannot put 1 cent of postage or 2 cents, but also obviously you can put 3 cents of postage for 1 3-cent stamp. Okay, now just thinking for a little. Of course, you can't make 4 out of these. That's not possible. And certainly 5 cents is possible because you could put a single 5-cent stamp on it. And like we said before, 6 is possible because that's 2 3-cent stamps. So then you say, what about 7? And think about it for a minute and just make sure you believe it's not possible. But you can't make a 7 out of a combination of adding 3s and 5s together. So that is no good. 8, on the other hand, you can do 8 because 3 plus 5 is 8. Right? So 1 of each gives you 8. Okay, and then 1 of each also gives, sorry, no, what am I saying? 3 of these will give you 9, so this is possible too. But for 10, you could just make 2 5s. Okay, and you can do this as long as you want. You can make 11 if you think about it. 2 3-cent stamps and a 5-cent stamp. But there is an observation that can be made at this point, which is that once we have 3 in a row, right, we have 3 in a row. Once you have 3 in a row in this case, you have everything because you could always just add 3-cent stamps, right? So once I know I could do this, I could do whatever's 3 steps later. And likewise from this, I can go 3 steps later, and this I can go 3 steps later. So what happens is it's all checks from here on out. Okay, and so what's happening here is some of the smaller numbers might not be possible, but at some point everything becomes possible. And this is the thing that we're going to sort of consider, and perhaps we want to know what's this point at which, beyond which everything becomes possible. It's the kind of question we're going to approach. So the postage stamp problem in general, I'm going to state. It's called the postage stamp problem just because it came from a question like this, but it's not necessarily literally always about stamps. And we're going to not necessarily just talk about the numbers 3 and 5. Okay, so the situation here is going to be this. If A and B are positive integers, the question is, what positive integers can be written as ax plus by, where, and there's the main thing that's going to make it different than what we were talking about before, is you can't use negative stamps. Okay, so x and y, we don't want them to be negative. Okay, so here where x and y are non-negative integers. Okay, and let me just, well, that's the question. And I use the word feasible over here. We'll just use that word here. So such integers are called feasible just in this discussion. So in this example, everything with a check is feasible, but 1, 2, 4, and 7 are infeasible, we would say. Okay. So this, actually, there is something, I didn't assume anything about A and B other than they're positive integers. In that last example, they were relatively prime to each other. And that kind of played a role. That means their GCD is 1. So if you did have A and B, which did not have GCD of 1, there would be certain numbers that are problematic because this expression is always a multiple of the GCD, right? Okay, so like if A and B are both divisible by 3, I can never write 1,000 as the combination of them because that's not divisible by 3. So eventually, when we do this, we're gonna reduce ourselves to talking about the case where A and B are relatively prime, and then that'll lead to a scenario like this, by the way, where eventually you hit a point beyond which everything is feasible. But again, if they're not relatively prime, what you're going to have is the only things that could be feasible are multiples of the GCD. So you wouldn't run into a bunch of check marks eventually like that. You would have just a check mark for every multiple of the GCD at some point. All right, but we're going to clarify what happens in general. Just another example if you want to think about something that's not stamps. It's just like maybe a sports game or something. So I was going to use football, but football does have a lot of ways to score, so let me simplify it and just say, suppose we were playing football, but we simplified it, and you could only get 7-point touchdowns and 3-point field goals, and that was it. Right? So suppose those are the only ways to score. Just another example to think about before we state any theorems. So suppose in a variant of football, a team can only score 3 or 7 points at a time. Okay, so then you could ask questions like what scores are possible and things like what's the largest score that's impossible to have. So you say what scores are possible. Or maybe a question we'll focus on a lot, what is the largest impossible score? So I guess using the word possible and impossible, like feasible and infeasible, I guess. But Anyway, so I mean, this, we'll learn the theorems to tell us the answer, but this is like this postage stamp problem as it was stated over here. I mean, we could just think it through if we like, just to see what happens, and then let's do this just so we can look back on it when we see what the actual answer is in general to such a question. So let's just put some numbers down. Okay, so we could say obviously 1 and 2 are no good. Okay, let's see, that's maybe enough. So we have, let's say, field goals and touchdowns, right? So field goal gets you 3 points. Not going to get 4 points, right? That's not going to work out. You can't get 5 in any way either. 2 field goals would get you 6. Okay, and a touchdown gets you 7. Okay, think about it. You can't really get 8 with no safeties or 2-point conversions or something like that. So no, can't get 8. You can get 3 field goals. That gets you 9 points. 10 is a common score, right? That's a touchdown and a field goal. Can you get 11? I do not believe so, right? That doesn't seem like that would work out. So no, you can't. They've done that for a while if you want, but that's not going to work. I don't think so. 12 is 4 field goals. This is a touchdown and 2 field goals, and this is 2 touchdowns. Right? And since we have 3-point field goals here, if you have 3 in a row, that means everything after is possible in theory, because you could always add 3 to these scores. So you get all checks all the time after that. So as far as the answer to this question goes, this would be the largest thing that's impossible, 11. And it was 7 over here. Okay, so anyway, this is the postage stamp problem. This is what we just call it in general, but maybe we want to talk about it with integers that are much larger than 3 and 5 or 3 and 7. And so we want to know, I guess, how do you find this largest impossible thing? And so we'll have a clean formula for it. We'll prove it. And let's state it. Okay, so anyway, here I'll just say, turns out to be the case, and we will eventually prove this, but let's just say it, is that if your GCD is 1, so if the GCD is 1, then the largest non-feasible value is going to be the following. It's A times B minus A minus B. So this, right, so anyway, this is asserting 2 things really, which we'll prove separately. It's asserting that this is not feasible. That number is not feasible, but it's also saying that everything after it is feasible. So anyway, that should work out in these 2 examples. We can just double check. Like if A is 3 and B is 5, that's 15 minus 3 minus 5, which is 7. That's this number here. Whereas if you have 3 and 7, this gives you 21 minus 3 minus 7. That gives you 11. It does check out for these, but we'll prove that. So like I said, this is really 2 separate assertions. This is infeasible, plus everything after it is feasible. And we're going to prove those in 2 separate statements. So let's look at, I think we can do one of them before we're finished. So we'll state this one formally. All right, so suppose, so we'll assume these are positive. We'll assume they're bigger than 1. That everything's kind of trivial if they're 1. I guess if one of them is 1, you can do anything. But anyway, suppose we have integers. Suppose these things are relatively prime integers. is that there are no non-negative integers x and y with the property that a times x plus b times y is this number, ab minus a minus b. Okay, we're going to prove this. There are no non-negative integers. So the thing is, what we're going to do is we're going to lean on what we know about Diophantine equations. So I mean, that is a linear Diophantine equation. It's just we're trying to put an extra restriction on it that we want the x and y to be non-negative. But if we loosen that up for a second, just think of it as a Diophantine equation where we could describe the x's and y's, both positive and negative, that solve it. Like we have a structure theorem that tells us exactly what they look like. And so if such an xy existed, it would also like fall into that form. So that's what we're going to use. So we're going to consider this Diophantine equation. Consider it as a linear Diophantine equation. And so, exactly that, but we're going to try to frame it in terms of what we just learned. We want to basically say something to get going that is like all solutions have a certain form. So I want to use our theorem to say that. But the way that worked was that if you're going to use that theorem, you needed to know one solution, right? So if you want to write down the general solution, you need to know one. And there is an easy enough way to produce one. I mean, you could think about Euclidean algorithms and stuff, but let me just point this out to you. So I'm going to point out a solution to you. So notice that if you take x to be minus 1, which if x is minus 1, that gives you the minus a, and then the other things are multiple of b. It's a minus 1 b's. So what we could do is we could take x naught to be minus 1 and y naught to be a minus 1. This is, in fact, a solution. Okay, so y, you can just plug it in and check. So if you took a times negative 1 plus b times a minus 1, and you simplified that, you would get the right-hand side. That's what it's supposed to happen. So you should have an ab, you should have a minus a, and a minus b. So anyway, that was perhaps, someone mildly clever to just observe this, right? So we pointed it out in the proof, so now that we know it, we can run with it. And so once we have this, then we can write the general solution in terms of the x naught and the y naught. So the general solution is therefore going to be that the x's should look like the one x naught we know about plus b over d times t. And d is 1 here. We're assuming everything's relatively prime, so b over d is just b. And then y is going to be the y naught we're aware of, a minus 1, minus a over d times t. And again, d is 1, so this is just minus t. So what this gets us then is, okay, so I guess we'll turn into a proof by contradiction or something, or maybe not exactly, but the point is then if you did have such a thing over here, right? So if you did have non-negative integers x and y that satisfy this equation, then the x and the y would have to look like this. Okay, so what we basically have to prove is that it's impossible for both of these to be non-negative at the same time. Right? For this formula and that formula to give you a non-negative thing at the same time. So let's suppose, we'll do it this way. Suppose xy is a solution with the property that x is greater than or equal to 0. Okay, what we'll actually do here is prove that y is negative. And so we'll show that y is negative. Okay, and that will justify that it's impossible for them to both be non-negative at the same time. Okay? So we just have to say, well, if x is non-negative, what does that tell us? Right? So let's write it above. Okay, so since x is non-negative, what that says is, what was x? It's negative 1 plus bt. Okay, and t is an integer. And so you're starting at -1, you're adding multiples of b to it, you get something non-negative. So what this tells us is that t is positive. Okay, this shows us that t is positive, because you can't, b is positive, by the way. Everything was assumed positive over here. So you're adding a multiple of b to -1 to go beyond 0. So anyway, this implies t is positive, strictly positive. Let me say it this way. Okay, it has to be strictly positive. But t is an integer. Okay, and that's kind of important. So a positive integer would satisfy that it's greater than or equal to, 1. Right, because there's no integers between 0 and 1. And so then what you get, so you know t is something that's at least 1. And then when you look at the formula for y, you realize that might be a problem, right? Because t is something that's positive and you're subtracting away multiples of a, this thing looks like it's going to come out negative. And you just have to show it does. Okay, so then what happens is that y is it's a minus 1 minus at, right? And the thing is that if t is at least 1, then this is less than or equal to a minus 1 minus a times 1. So you're taking away at least one multiple of a, possibly more. So this is as large as it could be. And then when you look at what this is the a's cancel, and this is minus 1. Okay, so y, this shows that y is less than or equal to minus 1. That's enough. It's negative, right? So we did this part here. Okay, so this thing will always be infeasible. Okay, this is a nice little proof just because it heavily uses our result on the structure of solutions of the Diophantine equation, just to show that these cannot possibly exist. Okay, but this is just half of the postage stamp problem discussion. It shows this is infeasible. We didn't show us the largest one yet. So something we'll do next time is show that anything bigger than that number is in fact feasible. And that'll wrap up our postage stamp discussion. Okay? Just let me know if you have questions. Have a great weekend. Make sure you